In this tutorial, we will be discussing the clausius-clapeyron equation. You'll notice that as the temperature increases, the vapor pressure also increases. However, this isn't a linear relationship. The vapor pressure actually increases far faster than the temperature. This is called an exponential relationship. If we take the natural log of the vapor pressure and we put it versus 1 over temperature rather than just temperature, it starts to create a straight line. And that's how we get the clausius-clapeyron plot. The clausius-clapeyron equation is used to find the delta H of vaporization, and it can be used to determine the vapor pressures of pure liquids or solids. And the slope here is the heat of vaporization over the gas constant. And this comes up with this equation here. The natural log of the vapor pressure of one temperature over the vapor pressure of another temperature. The delta H is the enthalpy of vaporization of if a substance is liquid, or an enthalpy of sublimation if it's a solid, and R is the ideal gas law constant. The Clausius-Clapeyron equation is used to find the delta H of vaporization. It can be used with two measurements. That's all you need. So 2 points on the plot of vapor pressure and temperature is to predict the vapor pressure of heat of vaporization, and the normal boiling point are known. So let's do an example of this. Here we have P1 and P2, T1 and T2, and the ideal gas law constant. Notice that this is in kilojoules and not joules, so it's times 10 to the negative 3 up here. We want to keep the 2's together and the 1's together on the equation. So the natural log of P2, which is 100.0 millimeters of mercury, over P1, which is 40.0 millimeters of mercury, is equal to the delta H of vaporization, delta H of this compound, over 8.314 times 10 to the negative 3 kilojoules per Kelvin moles times 1 over T1, which is 257, minus 1 over T2, which is 274. So first let's divide 100 divided by 40. So that's the natural log of 2.5. The millimeters of mercury cancel each other out. Delta H is what we're looking for. We're looking for the delta H of vaporization. 8.314 times 10 to the negative 3 kilojoules per Kelvin moles. 1 over 257 is 0.00389 Kelvin, 1 over T, 1 over Kelvin, minus 0.00365, 1 over Kelvin. Notice we have kelvins here and kelvins here. That means those are going to be able to cancel out in a minute. So the natural log of 2.5 is 0.916. Delta H is still what we're looking for. .00389 minus 0.00365 is 0.000240, 1 over kelvins. Those kelvins now cancel out when we divide these two. So I'm going to divide 0.00240 divided by 8.314 because these are multiplied. If I put this over 1, I'm not changing this number. This is a top number, this is a bottom number. So I'm going to divide that out before I go on. So 0.00240 divided by 8.314 times 10 to the negative 3 comes out to be 0.0289. The kelvins canceled out, so I have kilojoules per mole. Actually, moles per kilojoules. Now I want to get the delta H by itself, so I'm going to divide both sides by 0.0289. That's going to leave me with a delta H equal to 31.7. Since I'm divided by moles per kilojoule over here, these two units are going to flip-flop back to be kilojoules per mole. And that's how you solve the delta H of vaporization using the clausius clapeyron equation.